But we'll come to the last topic, the Jacobian, which is related to it, but there is a little bit more elementary because I suppose you learned about how to do Jacobian before. The only thing different is this textbook just give you a semi-derivation, just or justification why you have the Jacobian of this form. So, and it takes a little bit of thinking, but it's not too difficult. So we'll see if you can follow the logic. Okay, so the idea is you transform your coordinate system. Originally, supposedly you have a Cartesian coordinate, you transform to a general coordinate, just like section 3, right? And now you want to calculate the volume element, because that will usually involve in the volume integral in the new coordinate system. You have this dv, the volume element in the new coordinate system. So that must involve all the differential in the new coordinates, like dq1, dq2, etc. Right? But because they are general coordinate, you obviously that won't give you the correct volume. There must be something, so there will be a factor influence to give you the correct one. What we call the Jacobian, right? And so that's now, and you learn about this before, but this is just try to justify the form of this Jacobian, and that is basically this is the whole thing. Basically, is this volume. This volume is graphically you write it. It's basically in a hyperspace. It doesn't have to be 3-dimensional, but if it's 3-dimensional, it's just basically you have 3 vector. You have it doesn't have to be starting from the origin. It's just dq. Or you can say it's just what we'll use just vector that transform from the unit basis vector multiplied by the differential. So this is like epsilon 1 vector dq1, right? And then you have a bunch of this vector. This is not unit vector, yes, it's basis vector. Right. 3, 3, 3, right? A bunch of this this differential vector, you can say. And the volume is basically is you can form a well, I don't know the proper name of that parallelogram. Is a for 2-dimensional parallelogram. But, it's hyperparallelogram, something like that. So basically, this is the volume formed by this vector, or this vector. What you try to calculate is dq. Right. This dv. The volume of that is dv. Okay, and now we can generalize that a little bit and look at the formula. So now forget about they are this differential, just any vector, any vector. So you have like 3 vectors or 4, I mean a number of vectors, A1, A2. Now go back to geometry, A2, A3. Right. And how you calculate it can be more. How you calculate the volume by this hyper volume. And the claim is that this dv, this volume is just the determinant of the all this component of this in back to the original original Cartesian coordinates. So this is A1 in the A1 vector in the x component, A1 y component, and z component, and so on, right? And then A2 y up to any number of dimensions. Z, whatever an x. Y, this is y. Right. So the claim is that the volume formed by this parallelogram is given by this determinant. So it's okay that's the claim. Then this, I mean, no, it's not differential. It's just the volume. Right? Can you see that that is the case? Or, I mean, can you justify that? How to divide is divide is a strong word. Doesn't have to be. I mean, the text will actually not divide. It's just describing a way to look at why this is so. Can you see that this is a volume? You also say that why how this
dimension is
a dimension is like that's one way to look at it. That's good. You know, you can look at certain property, and another property is that if two of these vectors are linearly dependent, which is just like A1 is proportional to A2. All the element A2 or A1, they are proportional to each other, then this will be zero, right? Because that's just the property of determinant. If one row is proportional to another row, then the determinant is zero, right? You know that, right? Yeah. So it means in terms of this geometrical picture is that if two vector of this in this hyperspace they are parallel to each other, obviously this whole volume will collapse, right? Because these two vectors just go to the same direction, just the whole volume will become zero. It's collapse the whole volume, right? And that's applied to any two vector. They are proportional to each other, so that has a property similar to a volume. Obviously, right? The determinant has the same property as this geometrical picture of a volume, right? So that's one property that give you this idea. Another is just to look at example. So obviously the volume is the easiest one is 2 by 2, right? So you have the A1. Just now you just have two vectors. It's A1, A2, right? Right. And the determinant would be just like this is x is one, right? And x, A2, A1 y, A2 x, A2 y, and we came that this determinant minus A2x would be the hyper volume becomes the area in this case, would be this area with a sign. So the sign did obviously we interchange A1 and A2, change the sign, and that quite obviously whatever formula you use that would. So this is not exactly the common sense definition area we usually think this is positive, but in this case, it's the area that's using this vector. This vector has directions, so this area we have a sign also. But anyway, with this will give you at least this area multiplied by a sign, right? And can you see how you justify that?
Since it's 2 by 2.
Yeah. I totally follow. And one way to do it is just introduce this is like a curl, a cross product. Another way to do it, go back to geometry. Say, you go back to polar coordinates. So this is like your theta one, this is theta two. So the component is just this A1x is just A1 times the magnitude times the cosine of it, right? And then A2 and y is the sine, right? Sine of theta 2 and minus 1 sine of theta 1 A2 cosine of theta 2, right? And then you group the terms A1, A2, and cosine sine, and sine cosine, that is sine of theta 2 minus theta 1, right? Yeah. So it's the difference between the two angles, which is this angle. Now has a sign, now it's the sign. This would be out. This actually is theta 1 minus theta 2, but you take just the absolute value, it doesn't matter. It will have a sign. Now if theta 2, because theta 2 is smaller than theta 1, this is a negative sign. That's just the way we do this definition of this A1, A2. If we define this A2, A1, then this would be positive, right? But it's the sign of this angle between the two vectors. And then you can say it's the projection of this, like the A1 vector. A sign is the length perpendicular to A sub 2, right? It's this length, right? The A sub 1 times this sine of this angle is this length perpendicular A sub 2. So basically now it's just A1 magnitude A sub 1 times A sub 2, and or like A sub 2 times A1 times sine, which is the height, what we call the height, right? It's just the geometrically the base times the height is how you calculate the parallelogram, right? The area parallelogram. So this is so this is right. Right. So that's in 2 by 2 is just what we expect, and 3 by 3, 3 by 3, A1 3, while A1 3. And we actually talked about that before when we discussed Levi's Hippolytus syndrome, and we claim that this is just a one dot and three. Right. And we already know that this is just basically the cost product. So that's just like now it's three dimensions here. So this is 1, 2, and 3, right? You have A1 and A. So how to say it? If if you have you put A2 and A3 on the plane, so A2 and A3, just like what we did in here. So you have A2, A3 on the same plane, right? And this is the direction perpendicular A2 and A3, which is the direction A2 cos A3. That's just the cos product. And you realize this is just what we had in the 2 by 2 matrix. So this will give you the area, right? With the sign, obviously, on this plane, right? And now this is A1. If you take a dot product with this one and the direction A2 cos A3, which is this direction, right? You just get basically A1 magnitude times the projection of it on this angle, whatever you call H is. So this area multiplied by H would be the volume, right? and the sign of obviously there's a sign, right? So you check that this formula, this way to look at this is satisfied in two by two matrix, 3 by 3 matrix, or 2-dimensional space, or 3-dimensional space. Now you can generalize that to n-dimensional space, and the reason to do that is this basically saying that you can diagonalize this matrix. So these are all vector. So you have a bunch of vector. 1, 2, 3, 8n, right? And you actually don't need to go all the way down, although your text would go all the way to diagonalize it. But the final step doesn't matter. What you do is you choose a vector that has one component or x component that is non-zero. Obviously, you cannot have all vector with 0x because that would give you 0. Right, so you at least have one vector that has x component non-zero. Then you add and subtract something multiplied by this to all other vectors. Right? Basically, you're saying that you get, say, whatever the x component. So this is the x direction. You make you transform, you use this A1 with a non-zero x component, and you add and subtract to all these other vectors, such that so A2 plus, say, alpha 2, A1, to cancel with the x component of this vector, so that after you do this transformation, after you do this addition, all the other vectors are perpendicular to x. So they have no x component. So that would form all these vectors from 2 to n will form whatever the hypervolume will form a hyper area perpendicular to x, right? So, and that would not change the total volume formed by all these vectors because just like here, or whatever you add A1, so just like what we did, just add A2, subtract this by just basically deform this, right? And so you have A2 and you get change this vector to here, basically get rid of the component along A2, but the area doesn't change. Change this vector to here, the area, this square is the same area of this parallelogram. Okay, well, so whatever this operation doesn't change the total volume. So you just add the something proportional to A1 to all the other vector, so that all the other vectors are perpendicular to x, right? So that operation does not change the volume. And similarly, this matrix, you do the same thing and write it in the matrix form. So basically, you get rid of all this. The first column will be all 0. After you change that, you basically change all this coordinate, but the volume doesn't change, but the first column becomes just the first one is non-zero, and the other is 0. All right. Then obviously the volume will be whatever this hyper area multiplied by the projection of this A1 vector on the x-axis. So which is A1x times the hyper area, right? Which is in the determined form is A1x times the rest of this matrix, which is this subdeterminant, right? So A1x times this one, and that volume doesn't change, right? And then for this determinant, you do the same thing as the one before. You diagonalize this sub matrix. So not diagonalize, just get rid of the first column. Make the first column 0 except the first one, right? And then you keep doing that. So all the element below the diagonal line will be 0. right? And this operation involving all this subtraction of vector does not change the hypervolume. Okay, and now the determinant obviously is just this multiplying the you don't actually need to diagonalize the although you can but that is not needed because the determinant obviously just multiplied by all the diagonal, right? The determinant is just this sum over a 1x. Now it's a2 prime because it changed all these a2 prime y, right? And so, and that is the correct volume of this one. So that's and then because determinant doesn't change, volume doesn't change, so the original one with all this diagonalization is obviously just the same as the original formula is correct in calculating the volume, even without the diagonalization. Okay, so that is his justification, right? And so this is how you calculate determinant in terms of the geometrical picture. This A1 is just the projection on this axis, and then the rest is this hypervolume, hyper area. So that's so A1x multiplied by this one. But then to calculate this hyper area, you do the same thing again. You get A2y prime. So and multiply by the subspace or sub area, which involves just the rest of the matrix. So this is just the way to, even in the geometrical way, how you calculate the hypervolume. Okay, by all this subtraction of vector and get all the diagonal elements. It's exactly the same way you calculate hypervolume. All this one, it actually doesn't matter. All this because say like the first one is you have this a sub 1 vector which has the x component and maybe other components. It has other components which are perpendicular to x. It has component on this area also, but the volume involves just a1 project on the x multiplied by this hypervolume. All the other component does not involve in calculating the volume because these are parallel to this area, and all the parallel component doesn't contribute to this hyper area that we already said that this just like here you move if you move it on the same plane doesn't change the area. So you move this area on the same plane, it doesn't change the area. So all these elements doesn't involve in the volume. This I didn't set diagonal. I didn't set down those. Although you can just like your textbook do the first step, like you can use last row to cancel these. Like whatever the row, you just multiply the whatever subtract by a constant times this element. Subtract this row from this row, multiply by a constant. You can get rid of all this zero, make it all zero except the last one. You can do that like the last step in your figure 4.2, but that actually is non-essential in this calculation because the calculation of this volume, like the first element, involves just the projection of this vector on the x-axis, which is perpendicular to this hyper area. Just this component multiplied by this hyper area. You don't need the other component of A1. Is that okay? It's just like what we did in here, or the three-dimensional space that we discussed. Yeah.
So if there are n elements, is this still a three-dimensional problem, or is it an n?
It's n-dimensional problem. You have n.
So
it's hypervolume, what we call it, right? So I think what you're asking is I'm not doing exactly as a textbook. The last step I'm saying that it's not needed. right now. But anyway, now go back to our original problem. Except this A1 or this A1, A2, A3 are just epsilon times the dV. Now dV is just epsilon epsilon 1. We'll go back to our definition. Epsilon I is partial xi partial qi and ex ei and aj some j ej, right? So the projection of this e sub I epsilon I in the Cartesian unit vectors are this derivative, right? And then you multiply by dqi. No sum. This is not sum over I. It's just multiplied by dqi. Right? So we want to calculate the volume using these exact. I mean, instead of A1, A2, A3 using this method. Okay, and then project on the component on the Cartesian unit vector and write the component in this matrix. Right. So obviously this becomes dx1, dq1, right, and dq1. And next element is partial x2, partial q1, q1, right, and whatever that number of elements, n q1, q1, and partial x2, still one, q2, q2, x2, q2, q2, and q2, q2, and so on. And also partial xn, partial kx1, partial q2, n, 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 qn. Okay, according to our discussion, this will be the volume that kind of spanned by this all these vectors. Okay, and now you can take all this dq out, and the rest is the determinant of this matrix, and what we call the transformation matrix. This is just the transformation matrix. This is just the transformation matrix, and calculate the determinant. Oh, I see. I don't know what your proper label of determinant that matrix multiplied by dq1 dq. And that is what we call the J. Right, that's going here. And sometimes, actually, it's quite common, we define this J as the absolute value, because usually we consider volume as positive definite. So we might as well do another absolute value here, because determinant can be of positive sign, negative sign. So, but you take another absolute value, go into J. And the reason is that we want to do a volume element, volume integration. If we consider dV as positive, you just need to make sure the limit of your area or the hyper volume will make sure that this is positive. So because your dq1 will be say q1 min, q1 max, right? And so on. It might be more complicated than that, and all are the same in terms. We have a J here. If J is defined positive, all you need to do is make sure that this Q min and Q max are chosen properly to make sure that is positive, right? So therefore, you don't need to worry about the sign of this determinant. It can be positive or negative, but you just take the absolute value and use the limit to choose the correct sign. Okay.